Our next presentation is entitled Hot Dip Galvanized or Metalize Your Bridge for Bridge Preservation and Current Case Studies. There are two presenters planned over here. One is Sarah Wilson of Illinois DOT, Tim Woll. I assume you're also from AZZ, is that correct? Sarah Wilson is a registered professional engineer in Illinois. She has 31 years with the Illinois Department of Transportation. Since 2002, she has been the Chicago Metro Region's bridge maintenance engineer. Tim Woll with AZZ has been with the galvanizing industry for 16 years and the steel industry for 22 years overall.
Thank you. I'm happy to be here, and I'm glad to be presenting what I believe is to be a bright spot on Illinois' future bridge maintenance plans. So we're going to talk about steel bridge preservation, which I think is near and dear to all of our hearts. So a brief outline, I wanted to talk about why should we care about bridge preservation. I realize this is probably preaching to the choir, but I really think we need to think how to sell it. Because when we're saying we want to do something different, we want to spend a little more money, we need to sell it to the people that don't understand, that really don't see what we see. You know, we need to think about right now, how can we preserve our steel bridges? What are we doing in the past? What should we do in the future? Ideally, I'd like to move all of our bridges to the Arizona desert because it looks like paint there lasts forever, but I don't think that's quite possible. We're going to talk about the Illinois experience, cover some of the issues, go over the costs, and talk about when should we do this work? When should we make this change? And then go over any questions you have. I think these pictures are pretty evident. Why should we preserve steel? Why should we consider different steel preservation methods? Because what we're doing isn't working. Either because we're not spending enough money on painting or we just need to do something different. We need something that's more robust. Painting isn't doing it for us. We also have a huge inventory of steel bridges out there. 30% of the nation's bridges are steel, and I'd venture to say they're the longer bridges, so I bet the deck area of steel bridges is huge. So what are our options for preserving steel bridges? Our standard in Illinois has been painting. We'll do a 2 or 3 coat painting system, and we'll declare victory, and our victory doesn't last very long. Weathering steel is an option, but it was sold to us as a good answer, but it hasn't always worked well everywhere, so we need to be careful where we use it. Another option we've used more in the last 10, 15 years is galvanizing and metallizing, and there's even in the future maybe a possibility of duplex coatings. Painting. What are some of our issues with painting? Well, it's really got a life cycle, and that life cycle is not the life cycle of the bridge. It's definitely finite. It's costly to replace that painting. And it's more costly than just the money up front. You've also got the lane closures, the traffic delays, and safety, the safety of the workers that have to be out there replacing that painting. We've had painters die in Illinois, and I'm sure every other state has probably had the same experience. This is a redecking, and 2 years after we redecked it, we did a full blast clean and paint. 2 years later, I've already got flash rusting showing up. Painting's not a permanent solution. You've got to keep coming back. Weathering steel? Well, weathering steel is it provides a protective patina that's supposed to prevent future rusting, but it doesn't always work. You got to be careful. It still needs a protective coating at bridge joints or at locations, bridge drains that see routine wetting. It shouldn't be used in humid climates. And it can cause aesthetic issues. Personally, I think it looks kind of neat with the rust bleeding down the piers, but not everyone agrees with my particular tastes. Well, one of the options we've looked at is hot dip galvanizing. It's not a paint coating, and it's not a zinc coating, it's actually a coating. So we're going to have Tim talk about hot dip galvanizing and metallizing.
Thanks, Sarah. So when we talk about the hot dip galvanizing, it's not paint, it's not plating. Technically, it really is not a coating. We're actually forming a new alloy. So how does that work? Well, it's a thermo-zinc chemical diffusion reaction that happens between molten zinc and steel. So for lack of a better term, We're actually melting the two alloys together to create a new metal that's going to protect the steel for a longer period of time. So how does that happen? Well, galvanizing is a factory-controlled process that is done on a repeatable basis, and you really can't fake it if you get to the end of the line and it hasn't worked. We know it pretty quickly and have to send it back through if that does happen. But how does that happen? Well, this is the process in a typical hot dip galvanizing plant. We have a degreasing system that happens initially where the steel is dipped just to remove grime, dirt, cutting fluids, things of that nature that have happened in production or shipping to the galvanizing facility. We then rinse that. It then goes into a pickling process. This can be either a hydrochloric acid solution or a sulfuric acid solution. It's about 50-50 in the United States. It's basically the preference of the galvanizer. Sulfuric lets you go a little bit quicker, but it's a little bit more aggressive, so you've really got to be careful. You've got to have a good operator. Hydrochloric, while it doesn't go as fast, you can leave it in there all weekend and it will not attack the base steel or the welds. So those are kind of the differences of the two, but they're both very effective in cleaning the steel to get it down to a white metal. If you read a paint spec, it says blast to a near white finish. To galvanize, we need to have a white finish. We then rinse the acids off again, and then it goes into a flux solution. This prepares the steel to go into the kettle to accept the zinc. So after it comes out of the flux solution, it does need to be dry. It's like when you go to McDonald's and you watch them throw frozen French fries into the hot grease. It spits, it spatters, it goes crazy. You don't want to be around that. So what we let it dry before it heads into the bath. It then goes into the bath where it is dipped and reaches 830 degrees, and I'll explain a little bit more of the specifics here in a second. But it reaches the temperature, it's galvanized, it comes out, it has to cool to the touch. Sometimes some galvanizers will quench or passivate the steel. Otherwise, we just let it air cool. And then it's inspected, cleaned, and then ready for shipment. Basically, it's got to be cool enough so you can put it on a truck so it doesn't burn the truck deck. This is a typical galvanizing plant. Down at this end is the pre-treatment line. This particular plant is not an inline plant, so the steel is then moved. That shroud area there, the blue and the gold area, is the kettle. That's a cover around the kettle, so in case the steel was not dry going in, it protects the workers there as the steel is dipped, and then it's moved out, and then this kettle that it's just about to go into here after coming out is the quench tank or the passivation in this particular plant, but that can be skipped if you don't want to do that particular step. So the hot dip galvanizing process, the steel is immersed in a bath, gets up to 830 degrees. That's where the galvanizing process happens. It's 98% pure zinc in order to meet the ASTM 123 spec. It has about 2% additives of aluminum, a little bit of bismuth, a little bit of nickel. It reacts with the iron to form the coatings, which I'm going to show you in a second. And the reaction is complete when that reaches that 830 degrees. When the steel is coming in, this is the metallurgical bond that is formed. So you have your base steel down here. You have your gamma layer coming in at 75% zinc and 25% iron. The delta then comes in the next level, 90% zinc, 10%. The zeta, as you can see, it's building out even larger here for 94% to 6% iron. And then your eta layer, which is your free zinc layer, the 100% zinc layer. This is where you're going to see that the white powder on, let's say, a guardrail that's out on the highway or that type of thing. That is not a bad thing. That is not white rust. White rust is actually black. That does not make any sense to me, but that's the case. So when you see that white powder, that just means that the eta layer is starting to work and to protect the patina, to protect the base steel. This is another cross-section of a piece of steel. This is going to show the hardness that hot dip galvanizing gives you. Down here, you're going to see the base steel is at 159 on the diamond hardness scale. Your gamma layer here, though, is 250 Delta 244, Zeta 179. So these three layers here are actually harder than the base steel. And that's why it's very scratch resistant. It's not going to damage easily in the field. An iron worker is putting it up and he hits it with a file or a grinder even. Unless you see it spark, you have not hit the base steel. Zinc doesn't spark. So that's just something to keep in mind when you're on a job site and you see that. If they hit it with a grinder and it doesn't spark, they have not hit the base metal. And so it does not even need to be repaired at that point. And then your ADA layer, though, is very soft. That's the layer that is really going to do that initial protection on the steel. It's going to oxidize quickly, but then it slows down as it starts to reach into your lower layers. The metallizing or thermal spray, so this is another method of getting the zinc onto it for larger beams that maybe aren't able to fit in the kettle. For galvanizing. But it's just a positive and a negative wire coming through. It's then sprayed out with the clean oxygen and applied in a heat environment to blast. Basically, you're blasting it into the steel, and it's kind of similar to a welding procedure. Then we have a flame spray that does a similar thing with your wire coming out, but you have acetylene and oxygen, and it will blast it onto the surface as well. Again, it's great for repairs, but also for large members as well. This is an approved repair under 780, and the spec for galvanizing is the thermal or metallizing spray.
Yeah, I'm certainly not an expert on duplex coatings, but it's kind of the way it seems like maybe if you want to do belt and suspenders, you can do the galvanizing or metallizing and then paint it as well. And you get a synergy between the two systems. The paint has to deteriorate before the galvanizing or metallizing will even begin deteriorating. So if your galvanizing is going to give, your paint's got a 20-year life, well, you're 20 years in before the galvanizing is even exposed. And it also could be used if you're concerned a little bit about the areas that are more prone to appearance issues. We've heard that metallizing, and I've seen it, it's a splotchier appearance. It's not as aesthetically nice. I really think it fades pretty quickly in the first few years. But if you're worried about that, you could put a coating over the galvanizing. So it's an option for the future. They're talking that maybe you could get a 100-year life out of a duplex coating. We haven't tried it yet, but maybe it's something that we want to consider with a 100-year life cycle of a bridge. So I wanted to talk about the Illinois experience and what are our challenges with steel bridge preservation, because the bottom line is I want to preserve the steel. Our problems in Illinois are we're the Rust Belt. We have climate problems, and because of our freeze-thaw cycle, we decided we're going to spread salt everywhere, and we're going to spread it a lot. When you talk about how much salt goes down, when you're talking about the high-speed expressways, you're going to spread a lot of salt. You're going to spread salt from the first drop or first flake of snow to the last flake of snow. So there's a lot of salt going down, and even with that, because of the high-volume expressways, they don't let me out to repair expansion joints. So I've got salt on my beam ends and on the overspray on the beams from the bottom. There's salt everywhere, and there's definite problems with steel preservation due to our climate. One other factor is system age. We've got a lot of bridges that were built in the 50s and 60s. I'm sure every state does, as the interstate system was built. And, guess what? That steel's getting older. And, did we keep up with the painting? If we didn't, we're probably looking at replacing the steel. But in the future, are we going to have more money to keep painting on a regular basis? I couldn't even keep up with what I've got now. And as we build more bridges, I'd really love to have a system that I didn't have to keep coming back to. Again, insufficient maintenance budget. We got a lot of lead steel still out there. So guess what? Lead painted steel means a lot of environmental control, so that's an even higher cost of repainting. We've got urban high-volume roads in the Chicagoland area. Guess what? I can start painting about 1 a.m., and by 5 a.m. I have to be off the road. That's a 4-hour window. If you sat through the contractors talk about time equals money. With a 4-hour window, guess what? That equals a lot more money to paint than in areas of the country where you let them close that road for 3 or 4 weeks, and so they could work 24 hours a day if they wanted. So it's very costly to paint in the urban area. And then I've got an even higher challenge. If you've ever been to Chicago, if you've taken any of the mass transit, the elevated system with the electrified rail, it travels alongside many of the expressways, and many of the overpasses over the expressways crossed right over that electrified rail. Well, that electrified rail runs about 20 hours a day, and the time frame between trains is about 10 minutes. Guess how much time I get to paint? Not very much. So those are our challenges in preserving our steel. So we wanted to find something that would work. We needed a method to protect the steel that didn't require us to go back every 15, 20, 25 years to recoat it. So we looked at galvanizing some of the bridge replacements we were doing, some of the new rolled girders. We looked at the rolled girders first because they fit well into the baths. We did have to make some design changes to accommodate the baths. They were only a certain length, so we had to make sure that the lengths of our beams and where the splices were going to work with the bath lengths. So there's some planning you need to do ahead of time. And then as we looked at some of our larger plate girders, again, we were outside the limits of what could be fit in a bath. So there we turned to metallizing as, we saw it as not quite as good as or as hot dip galvanizing, but certainly better than painting. So our first use of galvanized beams was in 2002, and inspections 15 years later really hasn't showed much change in that. Since 2002, we've rebuilt over 30 bridges using galvanized or metallized steel, and we've seen no significant issues. And certainly when looking at the challenges that Illinois has, I think the advantages of galvanizing and metallizing are readily apparent. Again, I'm speaking to the choir, but someday you have to speak to the people that don't see it, and you have to explain it. This is the bridge. It was done in 2002. So it's been out there for 15 years, and we really don't see any problems with it. Again, love all the utilities that are under the bridge, so that complicates any work. This is another bridge that was done. It shows the electrified rail, and it does show one of the issues that we run into, and it's an aesthetic issue completely, which doesn't bother me because I'm a bridge engineer. I'm not there to make things pretty. I want to make them last. But you can see the dip line on the girder. This is one method they use to, if their girder bath was 50 feet, they could actually do closer to a 60-foot beam by doing a double dip. But again, it just leaves you an extra line, and I don't think it's an issue, but if it's aesthetically an issue to you, obviously you could look at that duplex coating option and painting that fascia girder. So here's one of our largest projects to date where we've used metallized and galvanized beams. This is I-55 at Lakeshore Drive. We replaced 6 bridges, just completed last year. Almost 15 million pounds of steel we went with galvanizing and metallizing. We did not want to face the costs of repainting in the future. And here's one that's currently ongoing. Illinois is working on replacing the Circle Interchange, now the Jane Byrne Interchange, in the heart of the loop of Chicago. 18 bridges are being replaced, and where the girders are small enough, we're hot dip galvanizing, and where they're large, we're doing the metallizing process. So Illinois is making a serious investment in the process. I actually hope that we can bring it beyond the limits of the urban environment, because I think it's, when you look at life cycle at all, it becomes readily apparent that if you've got a process that will last 50 to 75 years versus another process that takes 25 years, it's far better. Again, some of the design issues: limited tank size may require additional splices, plate girders may require some additional stiffeners, and some construction issues, they may require dipping and blotchy appearance, but it's really an aesthetic thing.
So I'm just going to do this real quick. So this is a cost calculator by the American Galvanizers Association. It's going to talk about Galvanizing's initial cost benefits, but the big thing is the life cycle cost savings for a typical project. This was done by a KTA Tater paper that was used. So they were the ones that presented this at the NACE conference, at the paint in 2014. Galvanizing used the AGA's information as far as U.S. average of cost, but this was the project over here, 50,000 square foot project. They were looking for a 75-year design life in a moderately industrial environment. They looked at a couple of systems for painting, but then galvanizing is a full inclusive pricing. And these were the numbers that came up with initial cost of $1.76 a square foot for an $88,000 investment. And then these were the paint down to the metallizing costs, where metallizing is great. It is expensive. And so you can see the difference in the total initial cost. But the big difference comes when we get into life cycle parameters and the life cycle of this thing done by KTA Tater here on the. And this was after 75 years. Galvanizing hasn't changed because there's been no maintenance to it, but with the repainting of all the different systems, you see the life cycle costing really moving up. And so this is where galvanizing can save you a lot of money long term. I'm going to move real quickly here to just a couple of bridges. This is a bridge, a truss bridge in New York. Over a stream. This is a really neat project, though, in Illinois, and the reason I like this is a floodplain, and you can see here that this has been up for almost 50 years now, and you can tell that the water has come above the ledge because of all the debris that's on there, but the galvanizing still has 5.5 mils. The minimum thickness you have to have on a beam this size, which is a 1/4 inch thick, is 3.9 mils when it goes into service. So even after 50 years, it still has 5 mils. The life cycle at 70 years in a heavy industrial environment for 3.9 mils of zinc. The Stearns Bayou Bridge in Michigan, again, was the first fully galvanized bridge in the United States in 1966. That's just me taking a picture of that, proving that that was done in 1966. But the beams here, you've got some gusset plates. This is actually a tube that's cut in half as a joining member underneath the bridge. This is the northwest side of the bridge, so it hits a lot of weather off Lake Michigan. The beams, to this day, we tested these 2 years ago at the 50-year anniversary, still have 5.6 mils on the beams on the most exposed side. But this right here is the railing that gets really hit with a lot of salt and snow from the plows. Still, even though it looks like there's no galvanizing left, there's still 2.4 mils because you're into those iron alloys that I talked about earlier in the presentation. So still 2.4 mils on this. This is a perfect system right now to go ahead and paint these railings to keep them in service. There is about 4 areas on the bridge that have this little tiny, spots that are really going to have to be a little bit more attention to, but it really can do it. And then one more real quick. 1970, this bridge was built in Indiana with galvanized one side and painted on the other side. It has been redone. It was repainted in 1984, the painted side was. And then in 2002, I think? Yeah. Early 2000s. In early 2000s, that painted had to be metallized and then painted. So you can see the amount of maintenance that has had to be done to this painted side, where the galvanized side, no maintenance since 1970, and everything is still doing fine. So if you have any questions now, we'd be happy to answer them. I don't know why Kevin put this slide in, but he did. So
I'm the chair of the National Bridge Preservation Partnership's Coatings Group. We pushed through a research project that wasn't easy, where we actually got recommended to be funded for duplex coatings, and hopefully by score, and hopefully it's going to go through. But I think you're right on the mark. I do think, though, that with the paint system, we should be trying to work on a high-performance paint system, try to gain as much life out of that. But you're right. I think you're headed in a great direction there.
In Florida, we already have probably like 5 bridges that we have used this technology, and we are seeing exactly the same results. Absolutely no damage on it. We also completed a in-house research recently, and actually we are publishing on this year's NACE conference, metallic coatings on structural steel, and we're getting very, very good results. However, I want to point out in our study, the metallizing actually did much better than the galvanizing.
Oh, that's interesting. I'm glad to hear that.
And we're going to be publishing the results, like I said, next week. One of the differences is the amount of zinc that you can deposit on the steel. With the metallizing, you get a larger millage. The other thing is, for anyone that is interested on it, NSBS, the National Steel Bridge Alliance, just published a specification for metallizing on structural steel. Just passing that as a piece of information.
Was that the National Bridge? That was the NSBA, right?
And the NSBA, yeah.
Let's have a round of applause for Sarah and Tim.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org.